Welcome to aminacademy.com. In physics, let us discuss about second law of thermodynamics. In first, we already discussed about the first law of thermodynamics is the principle of conservation of energy. Common experience shows that there are many conceivable processes that are perfectly allowed by the first law and yet are never observed. For example, nobody has ever seen a book lying on a table jumping a height by itself. But such a thing would be possible if the principle of conservation of energy were the only restriction. The table could cool spontaneously, converting some of its internal energy into the equal amount of mechanical energy of the book, which would then hope to a height with a potential energy equal to the mechanical energy it acquired. But this never happens. Clearly, some additional basic principle of nature forbids the above happenings. Even though it satisfies the energy conservation principle, this principle, which disallows many phenomena consistent with the first law of thermodynamics, is known as the second law of thermodynamics. That the second law of thermodynamics states that is a physical law based on universal experience concerning heat and energy interconversions. One simple statement of the law is that heat always moves from hotter object to a colder object for downhill unless energy in some form is supplied to reverse the direction of heat flow. Another definition is not all heat energy can be converted into work in a cyclic process. The second law of thermodynamics have two statements. In first, the Kelvin-Planck statement of the second law of thermodynamics. It is also known as the heat engine statement, states that it is impossible to devise a heat engine that takes heat from the hot reservoir and converts all the energy into useful external work without losing heat to the cold reservoir. However, we can imagine thermodynamic process which would conserve energy but which never occur in nature. For example, if we bring a hot object into a contact with a cold object, the hot object cools down and the cold object heats up until an equilibrium is reached. Second statement, the Clausius statement, was expressed as heat can never pass from a colder to warmer body without some other change, connected therein occurring at the same time. And the Kelvin-Planck statement as it is impossible to construct a device that operates in a cyclic and produces no other effect than the production of work. The statement of the second law of thermodynamics says this way now. The second law must apply to each of these devices, so consider two more elegant statements of the second law. Clausius statement further will discuss. It is impossible to construct a device which operates on a cycle and whose sole effect is the transfer of heat from a cooler body to a hotter body. Kelvin-Planck statements, it is impossible to construct a device which operates on a cycle and produces no other effect than the production of hard work and the transfer of heat from a single body. These two statements are equivalent effect. A reversible and irreversible process. We will discuss about a reversible and irreversible process now. In a reversible process, infinite changes occur in a system. In an irreversible process, finite changes occur in a system. In case of an irreversible process, the initial state and the final state of a system is never in equilibrium. The equilibrium is only achieved at the end of the process. In here, this xy axis, it shows that irreversible process is here and reversible process this way. Irreversible process is not always happen. Now, further we'll discuss about reversible processes. A thermodynamic process, state initial to state final, is said to be reversible if the process can be turned back to such that both the system and the surroundings return to their original states with no other change anywhere else in the universe. As we know, in reality, no such processes as reversible process can exist. Thus, reversible process can easily be defined as idealizations or models of real process on which the limits of the system or device are to be defined. They help us in incurring the maximum efficiency a system can provide in ideal working conditions and thus the target design that can be set. Now let us discuss about some reversible processes. Extension of spring. That means if we leave the spring, it will come to original position. It is reversible. Slow adiabatic compression and or expansion of gases. Electrolysis with no resistance in the electrolyte. The frictionless motion of solids. Slow isothermal compression or expansion of gases. Now we'll discuss about irreversible processes. An irreversible process can be defined as a process in which the system and the surroundings do not return to their original conditions once the process is initiated. Take an example of an automobile engine that has traveled a distance with the aid of the fuel equal to an amount X. For example, during the process, the fuel burns to provide energy to the engine, converting itself into smoke and heat energy. We cannot retrieve the energy lost by the fuel and cannot get back the original form. There are many factors due to which the irreversibility of a process occurs, namely the friction that converts the energy of the fuel to heat energy. We cannot go back. The unrestrained expansion of the fluid prevents from regaining the original form of fuel heat transfer through a finite temperature, the reverse of which is not possible as the forward process. In this case, is spontaneous. Mixing of two different substances that cannot be separated as the intermixing process is again spontaneous in nature, the reverse of which is not feasible. Thus, some processes are reversible while others are irreversible in nature, depending upon their ability to return to their original state from their final state. Some example for irreversible process are relative motion with friction, throttling, heat transfer, diffusion, electricity flow through a resistance. We have done. Please subscribe our YouTube channel.